Welcome to this video. So what is the roadmap of scientific computing with Python? Before answering that, let me ask you something more basic. How we communicate with each other? Answer is through a language that both people understand. Now, if I ask you, how do you even talk to a computer? Can you just tell it in English, Hindi, French? No, computers don't understand human language directly. They speak in code, and to talk to them, we need a language they understand. Python is one of those languages. A way to communicate with machines. We have other languages like C++, Java, Fortran, etc. So in this video, we will walk through the entire journey from Python basics to advanced simulations with real-world examples. We divide this journey into 4 segments. Our first session is about basic Python, where we will learn about variables and data types, list, tuples and arrays, loops, for, while and conditional logic if-else, functions and user input. So I know this is a new term for freshers for Python. We will understand this with analogy of kitchen. So let's imagine Python as a fully functional kitchen. Before cooking, you should have knowledge about kitchen tools, raw materials, spices, etc. So before using Python, you also need to know about variables, lists, tuples, arrays. In section 2, libraries. So Python contains 350,000 libraries like NumPy, Pandas, Flash, Django, Matplotlib, etc. to support any project like web data science, games, automation. Here we are not going to explore all of these libraries. We will focus in our scientific computing and only learn the required ones that are more than enough to handle any physics, mathematics or statistical problem you will ever encounter. So first one is NumPy, which is numerical computing backbone. Second is Matplotlib for scientific visualization. Third is SciPy. SciPy is scientific computing toolkit. Then SciPy. SciPy is specifically for symbolic computation. We will understand libraries with more easy example or more easy analogy. Let's say you are confident enough about basics of kitchen utensils, but the problem arises if I ask you to bake a cake. Can you do it with only the knife and a pan? Well, you can try, but it would be unnecessarily complex and frustrating. So in this case, you need an oven and a specialized tool. So in Python, that specialized tool is called a library. These libraries accelerates your work, make things simpler. You can solve a complex problem with ease. The best part is the Python library can solve many different types of problems once you understand it properly. Exactly like with oven, you can bake not only cake but also bread, french fry, dry chicken, etc. NumPy is one of the best libraries for scientific computing and data analysis. So NumPy, the pressure cooker of scientific computing. With NumPy alone, you can solve physics, mathematics problems more than enough. Whether it is linear algebra, vector calculus, differential equation, quantum mechanics, NumPy is your fundamental tool for number crunching. So after cooking, what next? You also have to serve the food beautifully. That's where Matplotlib comes in. So you find dinnerware set. Whether you want to visualize results, compare graphs, or make 3D animations, Matplotlib does it all. Matplotlib is a huge dinner set you can visually represent and any complex data, any complex problem, from plotting sine waves to visualizing statistical histograms or animating differential equation. Matplotlib is your go-to library for scientific visuals. Let's come to the another library, that is SciPy for hardcore simulation. Think of SciPy as an extension of NumPy. It's built for hardcore simulation, deep numerical analysis, optimization, integration, and solving differential equation. Whenever a problem is too advanced for NumPy alone, SciPy steps in. And finally, let's talk about SciPy, the advanced automated instrument for cooking, designed for symbolic computation, for advanced physics simulation. So basically, it already knows what is Boltzmann constant, delta function, Taylor series, and polynomials. Unlike NumPy and SciPy, which gives you numerical values, SciPy gives you the mathematical truth, the exact algebraic simplification. It does step-by-step symbolic derivatives, analytical integration, equation solving without numerical approximation. It's like working with the equations in your physics book directly in code. We will discuss it later. Section 3 is operations. Now that we understand Python basics and the major libraries, the next step is to apply them to real mathematical and scientific operations. So this is where the real power of scientific computing begins. So we will cover the following operations step by step. So the first one is linear algebra. This is the foundation of modern science and engineering. Applications are image processing, quantum mechanics, solving systems of equations. Then vectors. Vectors represent quantities with both magnitude and direction. From simple displacement in physics to high dimensional data in machine learning, vectors are everywhere. Third one is differentiation, the tool for measuring the change. Examples are like velocity from position, reacting rate in chemistry, the rate of population growth in biology, you can see. Fourth is integration, the tool for adding up small contributions to get the whole. Examples are like calculating the distance from velocity, total energy, or the area under the curve. Then ordinary differential equation, the equations that describe how systems evolve with time. Whether you are modeling radioactive decay, oscillations of a pendulum, population dynamics, the ordinary differential equations are everywhere. Then Fourier transform. So Fourier transform is a way to look at signal in terms of their frequency components, analyzing the sound waves, MRI image reconstruction, solving partial differential equation in physics. So you need that Fourier transform. Then interpolation, the process of estimating values between the data points. Then partial differential equation, the equation involving multiple variables and their rates of change like heat conduction, wave propagation, fluid dynamics, etc. Then tensor, a generalization of vector and matrices to higher dimension. So essential for general relativity, stress strain analysis in engineering and deep learning. Then complex numbers with real and imaginary parts, the alternating current and in electrical engineering, quantum mechanics, wave function, complex numbers are everywhere. Non-linear dynamics, many real systems are not simpler or linear. Okay, next one is vector spaces, the stage where linear algebra plays out, spaces formed by vectors, used heavily in quantum mechanics, computer graphics, and optimization. Next is chaos theory, systems that are deterministic but appear unpredictable. So basically, predicting the randomness. Now, Monte Carlo simulations, a method of solving problems using randomness, like radiation dose calculation, risk analysis, estimating integrals. So Monte Carlo simulations have huge application. Then stochastic effects. Unlike deterministic systems, some processes have inherent randomness, like stock market modeling, radioactive decay, molecular motion, etc. And finally, the analysis of experimental data. No scientific computing is complete without analyzing the real world data. So in this segment, we will understand how to analyze any experiment. So as a whole, we learn not only how to perform these operations in Python, but also why they matter in science and engineering. Together, they gave us ability to model, analyze, and predict the complex real-world systems. Our section 4, the last section, is simulation and modeling. So far, we have learned the basics of Python, explored important scientific libraries, and practiced common operations. So the next step is simulations and modeling, using all these skills together to create computer programs that copy how real-world systems work. In this step, we bring together Python basics like variables, loops, condition, libraries such as NumPy, SciPy, SciPy, Matplotlib, then subject knowledge from physics, math, engineering, or any science field. Here, we will simulate how planets move in space using Newton's laws. In biology, modeling how a disease spreads in a population. In engineering, predicting how heat moves through a material. So simulations don't just do one calculation, they show how things change over time. This helps us test ideas, make predictions, and solve bigger problems. At this stage, you move from just doing calculation to building complete models that can explain and predict real-life situations. So in our next video, we will start from basics. Stay tuned and comment your questions and doubts.